Okay, so let's say that I had maybe some kind of metal, maybe rod or something. Um, actually, it should be probably a metal, in Cartesian coordinates, not cylindrical, since yeah, it could be, yeah. All right. Okay, so I have some kind of rod maybe, and let's say that I have some heat flowing through this rod, right, in or out of this rod. So I might have some heat flow vector field, right, and we'll call that vector field F. So maybe heat is flowing this way out of the rod, or this could be like a certain segment, like a certain dV of the rod, and maybe some heat is flowing out this way into the air, but it's mostly just flowing this way, and we have some kind of heat flow vector field F. So we have this heat flow F, and F is equal to the heat. One sec. So it's equal to the heat flow vector field. Where each vector is like the direction and magnitude of the heat flow. And so what is the hold on. What is the heat flow vector field? Well, if we think about this, what we want to solve for is some function u of space and time, which is equal to the temperature distribution. That's what we're trying to solve for, the temperature distribution along this object, or made of some material. So the idea is that if temperature, we know that maybe this side is hot, and we know the heat flows from hot to cold, right? Second law of thermodynamics. So this is hot, and this is cold. I'm not going to use different colors too much, just because I need to switch back and forth. But so maybe it's hot over here and it's cold over there, and it's going to flow from hot to cold. Okay, so that's what we know, and we know that heat will flow in the direction that decreases your temperature the fastest. The reason for that is because heat just comes in when we have a bunch of vibrating and moving electrons and protons, right? Which are giving off EM waves or radiation. So maybe it's super hot over here or something. We have a lot of vibrating stuff over here, and then maybe over here it's like not as hot, but it's kind of warm. Maybe it's kind of warm over here, but then over here it's like barely any movement. It's super cold over there. So the question is, so we know that the heat will flow this way, right, towards the coldest. It will move in the direction that decreases the temperature the fastest. And the reason for that is because if these particles decide to move, for example, this way, since there's vibrating particles here, it'll bounce into these vibrating particles, and it'll bounce off and go somewhere else, right? And wherever it goes, if it bounces back this way, right, to the super hot area, right, warm, cold. So if it bounces back to the super hot area, but this is vibrating a lot, so it'll hit some particles and bounce some other direction. And it's warm over here, so the particles are still going to bounce around. So, but these particles, more of them will move towards the cold, since there won't be as many particles moving around at such high velocities to hit the particles and bounce them away. So more particles will end up, more of those protons and neutrons will end up over here. So that's why we move from hot to cold. This is kind of the idea. I guess I could just erase this now. So that's the idea of kind of how it works. So you have some more of an intuition of what's going on there, or at least that's how I think about it. So now, what we can do is we can say that the heat flow vector field F is equal to is in the direction is equal to the gradient of u. But the gradient of u would be the direction you'd have to move to increase our temperature the fastest. But it moves from hot to cold, not cold to hot. Cold to hot would be increasing our temperature, but it moves in the direction to decrease temperature fastest. So we have to take the negative. And it doesn't equal the negative gradient of U because for different materials, the heat will flow more easily through different materials, but it will still be proportional to the magnitude of the gradient of the temperature distribution. So we have to put a proportionality constant. This proportionality constant is just the thermal conductivity of the material that this object is made of. Because the greater this constant is, the heat flow vector field, the magnitude will be greater, so the heat will flow at greater velocities, and it will just and over time the temperature distribution will change faster. Like aluminum, it would like be comparing aluminum to something else where the heat doesn't flow as well. Okay, so now, so now we know we have this equation. So now the idea is, what we're going to do is, if I just remake this drawing maybe, if I had some kind of segment, we have a vector field F, right? This is some vector field F, and it could also be going into, and maybe it's coming in this side and coming out that side. So we know that F is equal to the negative gradient of the temperature distribution. And what do we know? Well, if I wanted to find the total heat flow within this object made of some material, well, what I'd have to do, how much heat is flowing out slash into this material? Well, in order to do that, I have some small dA here, right? Some small dA. And what I'm going to do is I'm essentially going to take the heat flow vector F, and I'm going to dot it with dA. And what that's going to do is it's going to tell me how much this heat flow, how much the heat flow vector field is coming out of this material made of some shape. And then I'm just going to sum up all these f dot da's everywhere, and I'm going to take the surface integral. And this right here would give me would be the flux, right? This is flux, right? And the flux of this would tell me how much heat is flowing in or out slash in of this object. So it is equal to the accumulation or total, we'll call it like the total heat flow. Total heat flow. Total heat flowing in slash out of object. Okay. So now we can rewrite this. Since f is equal to negative k times the gradient of u. We can rewrite this as the surface integral as negative k times the surface integral of the gradient of u dA, right, which equals total heat flow. Okay, so this right here is equal to here. Oh, my bad. And this right here is equal to we can rewrite this entire thing in terms of as a volume integral, right? And in order to do that, we can write it as volume integral, where we're summing up the divergence at every point everywhere within this material or object. So we can rewrite it as equal to the volume integral of the divergence of this right here, of the divergence of the gradient of here. We'll actually keep, what we'll do is we'll keep negative k inside the integral, because the thermal conductivity isn't necessarily constant, isn't always constant, especially as the temperature changes. Now, for a given range of temperatures, we can treat it as a constant because the difference is so small, but we'll find the general equation and simplify it at the end. So negative k times the gradient of u. We can bring the negative out here. That's going to be positive. So we get that divergence. We get the divergence is equal to the triple integral of the divergence of k times the gradient of u dv. It's the negative of this, which equals the total. And actually what we'll do is rewrite dx, dy, dz. dx, dy, dz, which equals total heat flow. And then maybe this is our system, so I say like within system. Actually, no, flowing. Or just say total heat flow. Okay, so this is our first equation, our first part of the equation, right here. And now the idea is we're going to now solve for the total heat flow through this object, and then but write it in a different form.